All right, guys. So this is the video tutorial for the simple harmonic motion and waves. I'm going to go over some problems from the assignment and some examples where you have a spring and a mass on a frictionless surface. Okay, so you have a situation like this. And let's say you move it or you stretch the spring some value x, which eventually is going to be the amplitude. Why? Because if the mass is here now, and you let it go, like initial, right? So the mass is, you have to stretch this, and you let it go, then you're going to have an equation that goes like this. Now, this is in the slides where A is the amplitude and YA will be X. So this will be the amplitude. Why? Because by conservation of energy, the mass will never be able to reach a point beyond that. So A, negative A, right? So the amplitude ends up being the point from where you let it go. And I'm doing this, I'm showing you this because there's a problem in the Cengage where you have to find parameters like the position versus time. You know that the velocity will be the derivative of that, which will be AW negative. And why is it negative? Because if you think about it, that negative for velocity is a direction, right? So you're going towards the negative x, so that's why. And then the acceleration is the second derivative will be negative AW squared cosine. Now, of course, you can use sine or cosine. At the end of the day, you have to use periodic functions. We use sine or cosine because they have a period. If you were to model this, right, in the x and y axis with the position versus time, then this one will be like this. I can keep going. Like that. A, negative A. And the distance between the peaks, that is the period, which is labeled with capital T. We should also give it a wavelength, which is why the period is 1 over the frequency, which is 2 pi over W. Okay? Well, we don't talk about wavelengths in this case because it's just a mass attached to a spring. So it's just a period of motion. The period can also be calculated as 2 pi square root of m over k. Where m is the mass and k is the constant of the spring. And then here, right? The maximum speed or the maximum velocity, V max, is W times A. And the maximum acceleration is, well, W squared A. Looking at magnitudes only. So taking absolute values there. Okay, these are just magnitudes. All right. phi is the phase, and we sometimes ignore that. Sometimes we don't have to ignore. We have to be careful because that tells you the position when t is 0. When t is 0, or here, when t is 0, the initial position is A. So when t is 0, cosine of what value give you 1? Cosine of 0. So in that case, yes, we can say that phi is 0. Now, if I want to model this with a sine function, right? I will basically, there's a phase, if you think about it, right? Because sine is will be like this. So there is a phase of pi over 2. So you will have to add, when you are shifted towards the left, you add pi over 2. So you could say A sine the same omega t plus pi over 2. So the 5, if you model this with a sine function, is not 0. Right? So you have to be careful with those little details in this type of problems or situations. And then there are a few equations that they don't give you in a textbook. For example, general equation for velocity. Right? You see how maximum velocity is like that? That's a particular situation. The general equation of velocity is W, the square root of A squared minus X squared. You can prove this, by the way. You know how you can prove that? By using the energy equations. So let's do it here. You see, we know that the maximum energy for a simple harmonic motion is 1/2 k squared. That's the mechanical energy plus the elastic potential energy, which is this. So if I multiply everything by 2, and I move this here, I get k parentheses a squared minus x squared. That's mv squared. If I divide by m, k over m is w squared. Right? K over m is, or this is that 1 over w. If I square it, it will be w squared. So w squared is times a squared minus x squared. That's v squared. If I take the square root, well, I get that equation there. Right? W, the square root of a squared minus x squared. So that's for a general situation there. Very useful. Sometimes you might need it. Okay. So some things that you can prove from equations that you are given in the textbook. So let's give some numbers. In one problem in the assignment, problem 9, they give you a mass, the spring constant in a frictionless surface, and they pull the block. I'm going to make it 6 centimeters from equilibrium, and it's released. Basically what I said here. So they ask you to find the amplitude. Okay, that's an easy problem. So you normally, I would suggest you guys write the equations on the paper size, because there are quite a few in this particular chapter. So in the problem, they tell you that the mass is, let's say, 1.5 kilograms. And is released from rest from the position x equals to 6 centimeters. So that ends up being the amplitude. And K is 400 newtons per meter. So part A is pretty easy. As I said, part A, the amplitude is just 0.06 meters. The position for which you release it. What's the angular frequency? So B, they ask you for W. Okay. Yeah, you have to use the equation. W is equal to the square root of K over M. Very important equation. All right, very important equation. That's kind of what I just showed you, right? Yeah, you have to use that. So K is 400, and this is 1.50. So this will be the square root of 400 over 1.50, which will end up being one goes 267. 16.3. What are the units? Rads per second. Well, that's what you did in circular motion anyway. The frequency. The frequency is the inverse of the period. If the period is 2 pi over W, the frequency is W over 2 pi. Well, that over 2 pi. So (2.60 hertz units of frequency? The period, the inverse of that. The period, capital T, is 1 over frequency. So 1 over 2.60, which is 0.38 seconds. Maximum velocity, WA. So para here, let's do it here. V max is WA. So 16.3 times 0.06. .98 meters per second. All right. Perfect. Yeah, you guys can see all that. And then the maximum acceleration, W squared A, right? So, what if the acceleration max is just W squared A, which is that square times 0.06. So that's just applying what we did, what I show you. 15.9 meters per second square. All right. So that's a nice example there. There's another one here. The spring mass system, guys, is not difficult. Even the simple pendulum is not, it's basically the equations that we show in the lecture, and obviously the ones I'm going over right now here in this tutorial. There is a question in Cengage that gives you the period of motion of a mass spring system. So let's say, example, if they give you the period equals to 0.65 seconds. That's the period. And the mass of the object is of 300 grams. Be careful with the mass and the units there. Find the frequency. A. Frequency is 1 over period. 1 over 0.65. That's it. $1.54 hertz. Find the force constant of the spring. Okay. The force constant is basically the constant, right? K. How do I find K? From the equation of the period that I just gave you, this equation. Period is 2 pi square root of m over k. Period is 0.65, mass is 0.3 kilograms, right? And k, I want to find k. So 0.65 is 2 pi square root of the mass in kilograms. 300 over 1,000 is 0.3 divided by k. So we divide by 2 pi, we square it. So basically, you have this. 0.65 over 2 pi equals to the square root of 0.3 over k. I square it. I want to square this here. I get 0.65 over 2 pi all squared. That's equal to 0.3 over k. And then k is 0.3 all divided by 0.65 over 2 pi square. Right? You can see that in there. So let's see, have to be careful with these numbers. So 0.65 over 2 over pi. Okay, so then that's 0.104. So 0.3 over 0.01 basically. Very, not bad. 30 newtons per. All right. And then if the total energy is 0.40 joules, find the amplitude of oscillation. So that's another easy question, right? I think I'll move it here. So if the total energy per se, if the energy, mechanical energy is 0.40 joules, what is the amplitude? To do that, you just make 0.40 equals to 1/2 k a squared. 0.40 equals to 1/2. K is 30 times A squared. So A squared, or A, is 0.80 over 30 square root. That's it. All right? Yep. 0.8 over 30 square root of 0.027. 0.16 meters. Remember, I used different numbers than the one in the assignment, so 2 problems there that we just did. Okay, this is a nice problem here. Let's talk about waves. Now we did 2 problems with oscillations. Now let's talk a little bit about waves. For a wave motion, I don't think you need the equation of the wave. I'm gonna write it here so you guys can see what parameters you may need. Like you still have frequency period, still sinusoidal. For a wave motion, the main equation is the one that gives you the relationship between the speed, wavelength, and frequency. Speed is equal to wavelength times frequency, right? This is the wavelength. What is the wavelength? Is how much it travels in one period. That's why if you use a sine function, use a sine function, you just look at the distance between the 2 peaks. So you have this, right? So you like have this is your wavelength. That is between the 2 peaks. That is why lambda is also V times period. Is the amount the wave travels in one period. Okay, so distance, you can do like that, you can do like that. And it makes sense because frequency is the inverse of period. So those are parameters that you can use. At the end of the day, there is a very important parameter, which is the wave number, which is K. K is not a constant anymore, it's just a wave number. Is how many waves are in a period. 2 pi over lambda. The general equation for a wave, by the way, if you're interested, is A amplitude sine of kx minus omega t plus 5. I'm just writing like that, where W is still your, angular frequency, 2 pi over period. Easy. And K is this. So K appears in the equation for the wave. Now, the problems of waves are not difficult. Like there's one here I'm looking from Cengage. They give you that wave, a harmonic wave, is doing 41 vibrations or I want to change it, 40 vibrations in 25 seconds. And the maximum, it travels 400 centimeters along the rope in 8 seconds. What is the wavelength? So they give information for velocity and period or frequency. That's how you find the wavelength. So let's actually move this. Let me see. Yeah, let's move this a little bit. Yeah, you can see the equations. So the problem, right, the example, they give you a harmonic, which is doing 40 vibrations in 25 seconds. You know why they give you that? Because you can get a frequency. Your frequency is the number of oscillations per second, or vibrations per second. So 40 over 25. Divide by 5, divide by 5 is 8 over 5. 1.15, 1.6. 1.6 hertz. That's the first piece of information. And then they give you the distance traveled by the wave, the harmonic, right? It travels along the rope 400 centimeters. So delta X is 400 centimeters in a delta T, which is 8 seconds. So 400 centimeters is 4 meters. So velocity is basically delta X over delta T. 4 over 8. 0.5 meters per second. Velocity, frequency. So lambda is velocity times the period. Period is the inverse of this. So 1 over 1.6. That's it. So 0.5 over 1.6. That's 0.31 meters. About 31 centimeters. Okay, let's give you now a figure. Like that. I guess I can erase. I mean, it's a video, so you can always rewind it, right? Go back to it. Waves and mass spring systems are not difficult. As you can see, we can do the problems very easily, just to know what parameters, right? But they give you here a wave. So another example is if they give you a wave. Like this. And they give you the whole value of this, which is 10.2 centimeters. And they give you this distance, interestingly enough. 4.2 centimeters. Find the amplitude, find the wavelength, find the period, and the speed of the wave. And look, they give you the frequency. The frequency is of 30 hertz. And the frequency is of 30 hertz. So how do you do that problem? As you guys can see better like this. So this whole thing is 10.2. And that's symmetry there. They don't tell you there is a jump. Be careful, because if you've done pre-calculus, you know that you can have a sine of 2 pi w, right? Or wt plus a phase, and outside plus a vertical shift. There is no vertical shift here. If there was a vertical shift, you will have to be more careful, because that means that this is not on the center. That's not the axis of symmetry. But the x-axis is the axis of symmetry. Because it's a symmetry, then 10.2 is double the amplitude. So the amplitude, part A, what's the amplitude? Well, from the figure, 2 times the amplitude is 10.2 centimeters. So the amplitude is just half, 5.1 centimeters. Okay? What is the wavelength? So the wavelength, remember, is the distance between the two peaks. Now, again, half the wavelength is this. If you look at the figure, right? So if that's half the wavelength, B, what is the wavelength lambda? 1/2 of the wavelength is 4.2. Then the wavelength is 8.4 centimeters. Amplitude and wavelength then. Then this is for the period. That's why they use the frequency. Let's find the period. The period is 1 over frequency, which is 1 over 30. That is 0.033 seconds. Right? Yeah, 0.033 seconds. And then what is the speed? Speed is lambda times frequency. When lambda was there, 8.4 centimeters though. So you have to divide this by 100 to make it into meters. Why? Because frequency is in hertz, 1 over seconds. Meters per second would be like this. So 0, 0, 12, 25.2, divided by 10, 2.52 meters per second. Very well. Very easy. Okay, let's do a simple pendulum. All right. And one tricky one. So simple pendulum is just basically the equation 2 pi square root of L over G for the period. But there's one problem in Sandwich that gives you the following situation. And it's tricky because you have to think in terms of direction. So a simple pendulum is like this, right? You have a rope and then there's a mass. And then if you let it swing, you basically draw it like this. So there is a period. The period is 2 pi square root of L over gravity, where L is the length of the pendulum. And gravity, you know, is always pointing downwards. Now, for problems like this, we take the direction of gravity positive because it's inside the square root. L is always positive, so we take the direction of going downward as positive. So the problem here is that what if this is placed, like, if you just have to, if they give you the length, you can just apply the formula and find the period, right? But what if this, L is 7.6 or 7.50 meters? So on Earth, will be just that. But what if you place it in an elevator that is going upwards? So what if this is inside an elevator that is moving upwards? So you have to think in terms of forces, right? If there is no acceleration, so tension equals to negative m gravity. And we call that the apparent gravity, okay? There's no acceleration, it's just that. Now, if there is acceleration now, so you have T going up, here the tension. All right? Then that T plus mg equals to ma, where that's the acceleration here. That's Newton's second law. So T was this. So mg minus ma equals to mg apparent. Mass cancels. So the apparent gravity is gravity minus acceleration. It's all in vectors there, by the way. Now, I'm taking that downwards as positive, right? So when you do minus, going up is like being negative. So if the acceleration is, say, 4.5 meters per second squared, the apparent gravity will be 9.8 minus that. Yeah, these I know can be a bit confusing. But it's because we are taking the negative as positive, like downward. Downward as positive, upward as negative. So minus will make it positive. So for part A, in that problem in Cengage, the period will be 2 pi square root of 7.50 over 14.3. That's if the elevator is going upward. We're going to see what happens when the elevator is going downwards. So here I have to use a calculator because it's 0.52. $4.53. So it's less, right? If the elevator was not, and think in terms of logic. If you're going up, right, there will be more drag for the pendulum to do this. So it makes sense that the period is reduced. right? Because the more gravity, the less period. Now, what if the acceleration is going downwards? If the acceleration is going downwards, right? This way here. So if the acceleration is going downwards, so you have the same elevator now going downwards. Same acceleration, 4.5. So the apparent gravity is 9.8 minus, and this is just minus 4.5. So there is less gravity. And yeah, think about it. If you are going down, that pendulum is going to kind of move faster. It's less drag. All right, so that's the only problem in the assignment that I feel might confuse or might be a bit, different. And there's another section in this problem, 1.42. $7.48. So yeah, way more period. So yeah, the period is taking longer now than that. You're reducing here as you're going up. It's increasing as you're going down. So that makes sense. What if the acceleration is horizontally though? If the acceleration is horizontal, it's in a track moving horizontally. So again, we're talking about vectors, right? So part C if this is moving 4.5, that is, well, guys, G there. Nah. There is your G apparent now. So your G apparent is a square root is a square square. All right. Let's move it here. That's what I'm talking about. If it's moving horizontally at 4.5, that is your G apparent. Right, you're getting at the other gravity is a vector, guys, right? It's a force, it's a vector. 20.25. Harness 16.29. 10.78. So this is getting 10.78. It's not going to be that different as if it was stationary, I guess, but it's a little better. So the period is just 2 pi square root of over. There you are. 7.50 over 10.78. Oh. 7.50 over 10.69. times 2 times pi. 5.22. Seconds. There you are. So I have a few problems we've done today for this chapter. I believe the rest of the problems are not so bad. As always, I will do office hours if you guys have any questions. All right. But this should answer most of the questions you have about wave, vibrations, and simple pendulum. Okay, so I'll see you guys later. I might throw you guys another video later with some extra problems, but for now, make sure you watch all of this and you start working on the Cengage chapter 13. See you later.